All right, welcome to worksheet number 5. We're going to talk about derivatives and rate of change. This corresponds to section 2.1 in our textbook. This is the first section of chapter 2. Chapter 1, we talk about concept of limit and how we can use limit. Here, we're going to start applying concept of limit to various situations. First, we're going to look at how we can think of the tangent line as the limit of secant line. So just like what's a tangent line, what's a secant line. If you look at the graph here, this line right here goes through 2 points of the graph. So there's one point of the graph, another point of the graph. So this is an example of a secant line. Tangent line is a line that goes through only 1 point of the graph. So I'm going to draw it later, but secant line, it goes 2 points or more maybe. And then tangent line, it just goes through 1 point of the graph. We'll also apply this concept to the situation involving motion. We'll talk about distance, time, and velocity, like a speed. And we'll see this example throughout the semester. So this is one of the most common application of the derivative. So again, let's look at this graph. I have my secant line here. It goes through this point, and it goes through this point. And first question is like, how do I find the slope of the secant line? M usually is denoting the slope, and then SEC for secant line. If you remember from back in algebra or whatnot, sometimes we'll label it like x1, y1. Let's label this point x2, y2. They're just different names, different ways to label these things. So you probably remember back in algebra, the slope m is given by y2 minus y1 over x2 minus x1. Sometimes this is referred as rise over run. Right. In this case, our case, x1, y1 is this point. x1 means just x coordinate of this point, which is a. y1 just means y coordinate of this point, which is f of a. Also, this point right here, x2 is the x coordinate of this point, which is just x. And then y2 is the y coordinate of this point, which is f of x, right? So I can rewrite this equation by using a and x and f of x and so on and so forth. So I can rewrite that as f of x minus f of a over x minus a. The reason I can do this is because this is my second point. So this is y2 right here, and then this is x2 right here, and y1 and x1, that's my first point. So this is like my y1, and this is like my x1 from here, right? So I can write the slope of this secant line as this. Okay, so we got the slope of the secant line. Now let's look at slope of the tangent line. We talked about tangent line before. So if I were to draw a tangent line, it's gonna be something like this. So instead of going through, so I'm gonna label it tangent line. Instead of going through the graph twice, like this first line we looked at, secant line is the line that goes through the graph only once. So it touches this point, but it doesn't touch anything else, right? So that line is called the tangent line. So question is, how can I find the slope of this tangent line, right? Well, in order to find slope, I need like 2 points, x1, y1, and x2, y2. But here, I only know 1 point. I don't know other points. I mean, there are other points, but I just don't know what number it is. Is it like 4? Is it like 5? What's the height? I don't know exactly, right? So how do I actually calculate the slope of the tangent line? Our strategy is going to be by using secant line. So let's say x is here, right? What if x was like somewhere here? Then I'm looking at this point, right? So if I were to look at that point and draw the line, it's not going to be exactly tangent line, but it's not going to be something very close to tangent line. What if my x was like even closer? Maybe I can use green here. What if x was right here? Then my point is going to be here. So this is not such an accurate graph. But if I connect this point and then the green point and then draw the line, it'll be very close to tangent line, but it's not going to be exactly tangent line, right? But I can kind of see how the slope is going to be very similar. So as I pick x to be very close to a, my secant line is going to be very close to tangent line. So we'll use the concept of a limit to basically get the slope of the tangent line. Let's look at the definition of the tangent line right here. Tangent line. Tangent line to the curve is given by, you see the limit right here. if you look at the formula itself, f of x minus f of a, x minus a, well, isn't it what we just got for slope of the secant line? That's exactly the same thing. But all I'm doing now is take the limit as x approaches to a. That means take this point, get close to a as much as possible, and see where it goes to, right? So I'm using the slope of the secant line to get the slope of the tangent line by taking the limit. So let me write that here. The slope of the tangent line is the limit of the secant line. Okay, let's look at example 1. It says find the equation of the tangent line to the graph y is equal to x cubed at x is equal to 1. So which point are they talking about? X is equal to 1, so 1 is here, so this is the point they're talking about. Tangent line, again, tangent line goes through the graph only once, so I'm going to draw it like this. I'm going to draw it as best as possible. So the question is, what's the slope of this? Again, tangent line, slope of the tangent line is the limit of the slope of the secant line. But here, let me just kind of play around a little bit. Let's look at sample points. So I'm going to put 1.01. So I'm going to look at the red line, which is the secant line, one of the secant lines, right? Here I'm just playing around to just plug in some random points to try to estimate what the slope of the tangent line is going to be. So this is my sample point. So we have a point 1, 1. So if I look at this point, x value is 1, y value is 1. And then we have a point and 1.01. And if I plug in 1.01 into this, it's 1.01 cubed. And I get 1.030301. So basically, I want to find the slope going through this point and that point. Well, we know the formula, so this is x1, y1, x2, y2. So y2 minus y1 over x2 minus x1. So that's 1.030301 minus 1 over 1.01 minus 1. Again, this is x1, this is x2, so x2 minus x1, so on and so forth, right? If I calculate that out, I'm going to get 2.9701 dot dot dot. So 2.9 something something. Again, that's not my final answer. That was just estimate, because we're supposed to find the slope of the tangent line, which is the blue one. Here I calculated the slope of secant line. That's really close to it, but that wasn't the tangent line. So the question is, what's the slope of this m? Again, the problem with this is I only know one point, this, right? I don't know, see, I drew it like this, but I don't know it actually goes through 2, 3. I don't know exactly what this point is going to be. This is my estimate, right? So how do I calculate the slope of the blue line, which is the tangent line? So I'm going to have to look at the limit. I have to use the definition. F of x minus f of a over x minus a as x approaches to a. In this case, my a is 1. I'm looking at this point right here. So let me rewrite this. Limit x goes to 1. So that's f of x minus f of 1 over x minus 1. In this case, our function is x cubed function. So let me just rewrite this. Limit as x approaches to 1. F of x is just this function, x cubed minus f of 1. I'm plugging 1 into the function, so 1 cubed is just 1 over x minus 1. All right, let me scroll up a little bit. Okay, so again, it's just finding the limit. My first instinct was to plug in 1 and see what happens. So let's say plug in x is equal to 1. What happens? Well, if I plug in 1 on the top, is 1 cubed minus 1. 1 cubed is 1. 1 minus 1 is 0. On the bottom is 1 minus 1 is also 0. So I get 0 over 0. Again, as we talked about it last section, 0 over 0 means we need to do something else. We don't know what the answer is yet. However, I have a polynomial over polynomials, so maybe we can simplify. Maybe we can factor things out and simplify. Here I see x cubed minus 1, and I can factor x cubed into x minus 1, x squared plus 1 over x minus 1. Right. So here what I did was I had x cubed minus 1. I factored that x minus 1 and then x squared plus, x plus 1. Oh, nice cancellation. Now I can plug in 1. So it's 1 square. Now I can plug in 1 again. 1 square is 1. 1 is just 1 plus 1. So 1 plus 1 plus 1, that'll be 3. So that was the actual answer. So my final answer is 3. When I so this is my tangent line. So maybe I should label that. This is tangent line. Tangent line. Whereas the first thing I was just playing around, this was the secant line, 2.971, right? So again, this was very close to this. So I could have kind of guessed that, but this is a precise answer. Let's look at the next formula here. It gives you alternate way to write what we just worked with. Sometimes this formula is convenient to use. Sometimes the other formula is more convenient to use. So let's look at that. It's like, where did I get that from here? They don't look exactly the same. Here, they're just giving you alternate way to look at things. Before, my a was here, my x was here, and we took limit as x approaches to a like this. So that's one way to look at. The alternate formula is basically there's h, and they label the next point instead of x, a plus h. So if you label it like this, if h goes to, here, let me write this, as h approaches to 0, basically it means a plus very small number. That means this point is approaching to this, right? So just alternate way to saying that this point is approaching a. One way of saying is just x is approaching a. The other way of saying is a plus h. As h approaches 0, this point is approaching to a. So that's basically what the alternate formula here says. Let me highlight it with the green here. So sometimes this is more convenient to use. So when they ask you to find this limit, you can either choose to use this formula or this formula. That should give you the exact same answer. All right, let's look at the next topic here. This is regarding the velocity, time, and the distance. So if s is f of t is the position of an object, so position is kind of like distance, right? So let me label it as distance. At the time t, so there's a distance, there's a time, and there's a velocity. It says instantaneous velocity. So velocity requires like a time period. Instantaneous velocity is just a velocity at exact point. It's given by this or that. So if you look at the formula here, they're exactly the same thing. If you look at the formula here, it's exactly the same. They use t for time instead of x, but other than that, they're the same formula. So this formula works for the situation where we try to find the instantaneous velocity. Sometimes it's known as instantaneous rate of change, so also known as AKA instantaneous rate of change. Instantaneous rate of change. So velocity is kind of like speed. Speed is rate of change. It just means how fast is your distance changing with respect to time, right? So it's an example of rate of change, and we'll use the same formula. Let's look at example number 2. Let s f of t 6t squared plus t plus 8 equation of a motion, t in minutes and s in meters. So again, t is a minute, that means this represents time, and then s in meters, that represents distance or position. Here, let 10 a.m. to be 10 a.m. corresponds to t0, so you're starting at 10. What is the instantaneous velocity at 10:05? So this is like 5 minutes later. So here I'm gonna say t is equal to 5 then. Let me sidetrack a little bit. I thought back when we learned that the speed is distance over time. Like Like, why do we have to use this complicated formula? Can I just use this? I'm gonna try to just use that and then see what happens, and then we go from there. So basically speed is the same thing as the velocity. So I need to find the distance, and then I need to find the time. Well, time is 5 minutes because it goes from time 0 to time 5. Time is 5, that's fine. And then I have to find the distance. Well, what was the distance to start? So when time is equal to 0, I'm gonna plug in 0 here. 0, 0 plus 8 is 8. So my position was 880. At time is equal to 5, what's my position? I'm going to plug in 5, so 6 times 25 plus 5 plus 8, which gives you 163. So I started from position 8 and ended at position 163. So distance travel is from 8 to 163, so 163 minus 8 will be 155. So basically 155 over 5, which is 31. This is the velocity, so it's distance per time, so that's meters per minute. That's my answer. But here at the so can we just do that? Here we have to. Oh, it depends on what the question is asking. Here it says what's the instantaneous velocity at 10:05. What we just calculated here is is the speed average velocity between 0 and 5. So we looked at velocity of the last 5 minutes. So I'm driving. So last 5 minutes, I drove 31 meters per minute on average. But because it says instantaneous, I'm gonna highlight that. So instantaneous velocity is like at 5 minutes, exact at 10:05, how fast were you driving, right? Not the last 5 minutes, but exactly at 10:05, that 5 minute mark, how fast were you driving? So in that case, I can use that because that involves the last 5 minutes. Here, I just want to see at that point. So again, how do I do that? I don't have a time. I don't have a distance travel. That's why we're going to use the formula here because it involves the limit. So let's look at that and then see if I can use that. So I was just playing around. This is not the real answer because I didn't answer the actual question. To answer the actual question, I'm going to have to go to the limit part. So in this one, let's use the second formula and see we can go from there. So let me scroll up here. The formula here is limit as h goes to 0, f of a plus h. A in this case is 5 because they wanted it exactly 5. So I'm going to say 5 plus h minus f of 5 over h. Okay, so I just copied this formula, this formula right here where I used 5 as an a, right? So this part, I have to plug in 5 plus h into the equation here. So this is going to be kind of slightly tricky. So 5 plus h squared, right? So instead of t, I'm going to write 5 plus h. So it's 6 times 5 plus h squared plus 5 plus h plus 8, right? And the second part is easier. I'm just going to plug in 5. All right, let's go from there. So limit as h goes to 0, that's 6, 5 plus h squared plus 5 plus h plus 8 minus, this part, so now I have to subtract minus this part, f of 5. So I'm going to plug in 5 into this equation. So 6 times 5 squared plus 5 plus 8. So minus 6 times 25 plus 5 plus 8 over h. That's a lot of writing. Okay, let's see, limit h goes to 0. Let's see if we can get some sort of simplification here. I'm going to rewrite this part, 5 plus h squared. That's 25 plus 10h plus h squared. So that will be 6, 25 plus 10h plus h squared plus 5 plus h plus 8 minus 6 times 25 plus 5 plus 8 all over h. The reason I wrote it like this long way is here is 6 times 25 minus 6 times 25, so that is going to cancel out. There's 5 here, this is 5 here because it's subtraction here, right? So that'll cancel out. There's 8, there's 8. Oh, nice cancellation. So what's left over? So 6 times 10h. So here, this part is kind of easy to forget to distribute. So 6 times 25, already did that. 6 times 10h, so that'll be 60 limit h goes to 0, 60h. Then what else? I did this, the 6 times h squared plus 6h squared. And then what else do we have? So I got this, and then there's h left, and everything else is canceled. So plus h all over h. All right, I think we're almost there. We're running out of space, but here I noticed that there's h, 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 and then h on the bottom, so I can cancel it all out. So here, let me h is h squared, so one of the h's will cancel out, and this will cancel out. So I get limit h goes to 0. I get 60 plus 6h plus 1. Okay, now I can take the limit as h goes to 0. So this will go to 0 because 6h as h goes to 0 will go to 0. So my final answer is 61. So 61 meters per minute is the instantaneous speed at that point. So from 0 to 5 was going 30 miles an hour, 31 meters per minute on average. But at that point, when at 10:05 was actually going way faster, 61 meters per minute. Let's look at the next example 3 here. Just a more conceptual question. What's the difference between average velocity and the instantaneous velocity? Sometimes we'll just call it velocity versus instantaneous velocity. The average velocity involves time interval, So we need like a time 0 to time 5 or time whatever to time whatever. So when we look at velocity, we're talking about over a certain time interval. Whereas when we talk about instantaneous velocity, again, I'm going to highlight instantaneous, we're just looking at a particular moment. So where it involves a particular time or moment, no interval, right? Just at that particular point, how fast was the car going or whatever, right? So that's the difference. All right, let's look at the next topic here. Here we're kind of looking at the formulas that we used before, because this is like one of the most important concepts of calculus. It has a special name attached to it. So f be a function defined in an interval containing a, the derivative, here I'm going to highlight this part, derivative of a function at a is defined by that limit that we just used. So again, derivative is most important concept. It's just limit. Graphically, it represents the slope of the tangent line. In terms of movement, it represents the instantaneous speed or instantaneous velocity or instantaneous rate of change. So since it gives you the slope of the tangent line, how do you find the equation of the tangent line? This is the equation of the tangent line, or we can also use, I like to actually use y is equal to mx plus b formula, where we can find the m is the slope of the tangent line, which we kind of use this formula to calculate. Again, part 2, the instantaneous velocity at time a of an object is given by f prime. So you notice that this notation, the derivative is f with the little dot. When I see this, I'm going to read it as f prime of a. Or I can say the derivative of f at a. Right? So I'll probably say f prime of a, but then what it is the derivative of a, f at a. Right? So I'm going to have you pause and work on number 4, example 4, to find the derivative. Basically, it's find the slope of the tangent line, right? So once you're done with, so work on example 4. And once you're done with example 4, let's look at example 5. Kind of similar to what we just did. We know, if you know the derivative of point is this, so they already gave you the derivative, so I don't have to find it myself. Find the equation of the tangent line at point 1, 2. Again, point 1 is x value, y is equal to 2 is the y value. Well, we know the slope is just f prime of a. That means plug in the derivative, find the derivative and plug in x value. So in this case, f of 1. We already know the prime. They already gave you the derivative, so I'll just plug in 1. So negative 2 over 1 squared, so it's negative 2. Oh, nice. So I know y is equal to mx plus b. Here, y is equal to negative 1x plus b. So basically, we're halfway there. This is the equation of the line. I already know the slope. How do I find the b? Basically, I can just plug in 1 for x and then 2 for y and solve for b. So I can solve for b. So here, plug in a point 1, 2. So this is x, y. So 2 is equal to negative 1 times 1 plus b. So 2 is negative 1 plus b. So b is equal to 3. So my final answer is y is equal to negative x plus 3. All right, I think this is it for this worksheet.